Okay, so the next lesson, we've got areas enclosed by the y-axis. You know what, if you can just jiggle your mind around a little bit and start thinking of replacing all the x's with y's and all the y's with x's, really this is very straightforward. What we've done everything we need to do, right, in the previous exercises. We've done everything we need to do. In this particular case, what we've got is some function, but instead of finding an area between this function and the x-axis, we're trying to find an area between this function and the y-axis. Okay, now we're really used to, and we want to find this area here, and it's still probably going to be from A up to B. They will be our limits. And we're really used to the idea now of thinking of everything being like y equals, I don't know, let's say x squared plus x. All right, we're really used to thinking of, of the function being y equals x squared plus x. And in this case, the function is going to cross over here at the origin and at minus 1. So it's going to be a parabola that looks like that. And the more sophisticated terminology would be to say that function f of x is equal to x squared plus x. You know, y equals something to do with x. That's what you do in years 7 and 8. And for most students, years 9 and 10, and even for much of year 11. And in some levels of mathematics, that's all they really do, is they just look at y equals something. But we need something a bit more sophisticated because we're going to do more complex work. So we've gotten used to the function notation, where we say that it's function f of x is equal to x squared plus x. And now we can, it's exactly the same thing. We're just substituting function f of x, a more sophisticated terminology, for y. Same sort of thing. But now, instead of thinking of y equaling a function of x, we need to think of it the other way around. What we really want to do now is we want to look at this as being x equals a function of y. So you could almost say from this stuff here, if we look at that, we're kind of saying y equals a function of x. That's what that's telling us. But we want to flip it around, and we don't want to think of it as y equaling some function of x. We want to think of our curves. If we're going to find the area between the curve and the y-axis, we want to think of these functions as being x is equal to a function of y. So that's not really all that hard for many curves, for many functions. A really easy example would be if y equals x squared. Well, if I actually want to make this as a function of x equals a function of y, then I do the inverse functions on each side of the equal sign, and I'll end up with y equals y to the power of a half is equal to x. So now x equals y to the power of a half. They're actually going to give you the same shaped curve. They'll give you the same, and you can use Desmos to check that out. They'll give you the same shaped curve. It's just that now we're looking at this in terms of x being a function of y. Okay, and previously what we've done is with the integral sign, if we had this and we wanted to find the area between the curve and the x-axis, you know, like we might want to find that area from minus 1 to 0, we'd have that the area is equal from minus 1 to 0 of x squared plus x with respect to x. That's what we'd do. The area is equal to that. Yeah, and that's the same as saying the area is equal, with the limits from minus 1 to 0, of some function of x with respect to x. That's really what we've got, isn't it? And if we take that one step further, we could really say that the area is, given these limits from minus 1 to 0, it's the integral of y, but with respect to x. So it's the integral of what y is equal to. That's what we've got. It's what y is equal to, but with respect to x. So in your textbook, what they're going to tell you is that when we do this, and you'll see it in other textbooks too, and it's not immediately obvious, I think. It comes with time and practice. In the textbook, what they'll often say is that we're trying to find the area will be equal to the integral of, with the limits from a to b, of x, but with respect to y. That seems all screwy. What is that all about? Well, we're kind of starting at this point here, and we're working backwards. So really, what we want is not x, because we're integrating with respect to y. And if we're integrating with respect to y, which means we're looking at the y-axis, that's the important, the key feature here is the y-axis. If we're integrating with respect to y, then we need to have a function of y in there. So really, we're going to have the integral from a to b of some function of y with respect to y. And now, it's starting to make a little more sense. We just need to know what this mystery function of y is, and we need to know what the limits are for the integration. All right, so now that we've kind of looked at that, all the other principles that are involved are still important. Sketch the graph of whatever it is that you're sketching. Have a look at the function. Sketch a graph of it. Carefully set out where the area is that you need to integrate. So I'm going to need my textbook here because I didn't actually write up some examples to do ahead of time. Set out where the area is, and then find the area that's asked of you. And I'm going to jump straight into one that's perhaps, oh, sorry, that's my phone. I'm going to have to pause you guys.